Okay, so what we're going to look at today is how to solve more complex linear momentum problems. In this type of problem, what we're going to see is that sometimes when you're solving a problem that's elastic, we don't know the two final speeds. So every question I've given you so far, whether it's been elastic or inelastic, you've always had all the variables except for one. So you just use one equation, you just simply isolate for the one variable, plug in the numbers, keeping in mind your plus and minus for the directionality, the vector nature of that. And what you end up with is a very simple way of solving these problems. Sometimes you can get a completely elastic collision and you don't know the final speeds of the two objects, but you can actually solve it. And solving it takes a little bit of work algebraically. However, it's not hard. It just takes, you just got to put in the effort to do it. So I'm going to show you three ways to solve it. One is the long way, sort of the algebraic method, the actual way. Two is using Wolfram Alpha, which will do the algebra for us, and we'll find the intersections that we're looking for. And the third way is using something called a change of reference frame. Now, your key learnings from the other day are going to come in handy about elastic or completely elastic collisions, and we'll see how that comes into play shortly. So we're going to do the example, and then you're going to do questions 1, 2, and 3 using Wolfram Alpha, and then you can check question 3 using the full algebraic method to make sure you can do it, and also check with the change of reference method to make sure you can do it. On the evaluation, you can use either of the three methods to solve the question. The change of reference method is super fast and doesn't require technology. Of course, the Wolfram Alpha will require a connection to the internet to be able to do it, and the full algebraic method will work, just take longer. Okay, so here's the problem. We have an air track glider of 3 kilograms, and it's moving at 2 meters per second to the right, and it's going to collide with another mass of 1 kilogram moving at 2 meters per second to the left. So this is our before situation. And after, they bounce off each other somehow. And we are going to try and figure out what V1F is and what V2F is. That's what we're trying to figure out. Okay, so that's before and after. And drawing these sketches is really important. Okay, so let's take a look. One thing we know for sure, and we've done this, is that momentum is conserved. So in a completely elastic collision, momentum is conserved. So we can very easily write the momentum equation, or the conservation of momentum equation, like this. And you're like, oh, that's fine. But you realize quickly we know everything except for V1F and V2F. So we have two unknowns, so we can't solve this yet. But we know something else about completely elastic collisions, and that is this. Kinetic energy is conserved. So if kinetic energy is also conserved, we can write another equation. M1 V1I squared over 2 plus M2 V2I squared over 2 equals M1 V1F squared over 2, like that. And you're like, okay, I know everything in this equation except for V1 and V2F. That is, two equations, two unknowns, you can solve it. Obviously, you're going to have to use substitution to do this. Now, I'm going to show you a better way to do this, just so that you don't lose your mind. Don't try and isolate it and substitute it in to this equation. It's going to be a brutal mess of algebra. So I'm going to allow you to, at this point, not like I don't normally allow you to do this, you're going to substitute values in, substitute it, and that way just the math will become easier. So let's plug in our numbers. 3 times 2 plus 1 times negative 0.2. So we're assuming that this direction is positive, equals 3 times v1f plus 1 times v2f. So this is 6 minus 0.2, which is 5.8. Okay, so there's our one equation. This next one, first step, multiply by 2. If you multiply both sides by 2, this 2 divides out, this 2 divides out, this 2 divides out, this 2 divides out, and we get rid of it. It's a really nice, easy way to do that. Then we can just substitute in the rest of the numbers. So we've got 3 times 2 squared plus 1 times negative 0.2 squared equals 3 v1f squared plus 1 v2f squared. Okay, this is 12, and then negative 0.2 squared is 0.04, so this becomes 12.04 equals, there you go. Okay, at this point, we're just going to isolate for v2f here. And you realize now that v2f equals this, and there's a v2f here. So we can take this, simply substitute it right there. That's it. So we do the substitution. So we're going to get 12.04 equals 3 v1f squared plus there we go. Okay, and now from here, don't panic, please. We've got only v1f that we have to solve for, and we just have to figure it out. So now the first term, we just square it. So 5.8 squared is, then for the middle term, we take this and this and multiply them, and then multiply it by 2. So it's 3 times 5.8, and then we multiply that by 2, and we get negative 34.8. And if you forget the math for that, please review your like squaring the brackets and like how you do that. And the last term, negative 3 squared is positive 9, and you have to also square the v1f, so you get this. Now let's collect like terms. We've got 9, 12 v1f squared minus 34.8 v1f plus 33.64. And then bring this over. Okay, so now I just flip this page over, and we're just going to write out the solution that we have so far. So far we have 0 equals 12 v1f squared minus 34.8 v1f plus, and then the last part that we had from the previous page was 33.64 less 12.04 is 21.6. Okay, now you're thinking, how do I solve this? Well, look at this. Quadratic equation. You think, oh, never thought I'd have to use that again, but you're going to have to. All right, so you've got an x term, a linear term, and a constant term. So in this case, we know what a is. A is equal to 12, b is equal to negative 34.8, and c is equal to 21.6. So v1f, or the x term that we're solving for, is minus b plus or minus the root of b squared minus 4ac all over 2a. And so minus b plus or minus the square root there you go. So there's two answers. There's two roots. Or now you don't be able to use your calculator to figure that out, but I'll give you a little hint. What you could do is you could Google very quickly something called a quadratic equation solver. And for the quadratic equation solver, you just put in your a term and you put in your b term and you put in your c term and you get the two roots. So one root is 2 meters per second and the second one is 0.9 meters per second. Those are your two roots. Now if you're thinking about the question, you're looking at it going, wait a minute. The solution, and this always turns out to be true, the solution to the problem is 2 or 0.9. Well, this was the initial speed of the object. That was the initial velocity of the object. That's not the answer. This one is the final state. This is the final state. That was the initial state. So that's what that solution right there tells you. Okay? Pretty cool that it does that. Now to solve for your V2F, you just use the equation from the previous page. 5.8 minus 3 V1F. And if you put that in your calculator, you go 5.8 minus 3 times 0.9 is 3.1 meters per second. And that's our solution. V1F is 0.9 meters per second, and V2F is 3.1 meters per second. Watch what happens if you put in 2 there. 5.8 minus 3 times 2 is negative 0.2. And negative 0.2 was the initial state of the second object. So we know that's not the answer. So we know it had to be this one. So those are your two solutions. It's not hard. And use the quadratic equation solver to figure it out. All your phones have it. So you can always check that. But you have to be able to write up to that point to be able to do it. Okay, let's use Wolfram Alpha to solve this problem. So how are we going to do that? Well, we're going to go to Wolfram Alpha and we're going to figure it out. So in Wolfram Alpha, we're going to write out the two equations that we have. So I'm going to go back to the sheet here and we're going to take a look at what we have. So when you're looking at the sheet, and there's an example on the back as well, on this sheet as well, you can go to it and it'll show you what to type in. So what we're going to do is, let's imagine that you can get to at least this first stage right here, or even this stage. Let's assume that you can get to here, and let's assume that you can get to here. Okay, so that's not too hard to get to. So you can write your momentum equation, and you can write your quadratic, or the quadratic part of the equation. It turns out that this will be an ellipse, and this is going to be a linear line, and the linear line intersecting with the ellipse should be the solution. So I'm going to type in this equation and this equation here. And you're like, okay, well, how am I going to do that? Well, I'm going to call V1F A, I'm going to call V2F B. I can call them whatever I want, but it just makes it easier if I call that A and call that B. So I'm going to write 5.8 minus 3 times A equals B. Intersects with, and then I'm going to write 12.04 equal to 3A squared plus B squared. That's my linear term. That's my ellipse. Hit equals. Make sure, hopefully I typed it all in correctly. And it's giving us the solution here. Yeah, these are the answers. It's just, it puts it in this silly form. Am I allowed to, yeah, you press approximate forms. There we go. Okay. So if you hit approximate forms, you're going to see there's two answers for the speed of A, 0.9 and 3.1. That's for A and that's for B. And the other solutions are 2 and negative 0.2. Well, we know that 2 and negative 0.2 are the initial speeds of both objects. So your solution for object A, or V1F, is 0.9, and for V2F is 3.1. Here's the really cool thing. This is your kinetic energy equation. It's an ellipse. And then the linear equation, which is your momentum, is this line. And there's two intersection points. There's an intersection, oh, it doesn't like when I do that. There's an intersection point right here at 2 and negative 0.2. That's the initial condition. And then there's one here at 0.9 and 3.1. That's the solution for A and B. So A is the 0.9, which we found is V1F, and B, which is the y-axis of 3.1, which is the other one. Pretty cool. So all you have to do is be able to get to this point, write out your linear term and write out your quadratic term, the momentum and the kinetic energy, and say intersects with, and you get your solution. The other option, of course, is to do all the algebra, which is not that bad, but you can do it. So on your sheet, if you want, you can write what we did. You can write down that we wrote down 5.8 minus 3A equals B intersects with, and I think we wrote here 12.04 equals 3A squared plus B squared. And remember, in math terms for linear, you write this. Okay, that's how you write it in latex form, or sorry, in the Wolfram Alpha form or in coding form to show a square or a superscript. Doing that will produce the two solutions. Okay, next one is called the change of reference frame. Okay, and we're going to take that one in just a second. Okay, so for this last solution, what we're going to see is what's called a change of reference frame. And the change of reference frame is going to be, let me just double check that that's still working. Microphone on. Okay. And so what we're going to see is how to solve this using what's called a frame of reference change. Now, this is a big mess. There's these two fancy equations that you see right here, and I explain to you how to use them. Now, if you wanted to go to the back pages here, you can see how solving these equations with the change of reference frame works. In order to do this, it's very straightforward. You can consider the special case of a completely elastic collision where the initial object of one object is 0. That's the key. So it's just any problem where a block hits another block or an object hits another block and it's completely elastic, but one of them is at rest. Then you do the algebraic method. You write out the momentum equation. Substitute in V2I is 0. Bloop, you get that. Write out the kinetic energy equation. Set V2I to 0. You get that. So it's exactly what we just did. We have equation 1, equation 2 with the momentum. We have the kinetic energy. Now, what I would have done in those previous problems is you start subbing in numbers, do the substitution, find out where they intersect, and you get the solution. What you're going to do here instead is we are going to actually do the substitutions. So we take this, we bring this term over, we collect like terms, we then rearranging 1, so we've got, we rearrange 2, rearrange 1, so we get 2 new equations. And again, I'm going over this very fast. You can look at it if you're really interested to see how it worked, but for now, we just want to save some time and just go through it quickly. And then you can divide both equation 3 by equation 4, like so. You know, a bunch of the terms divide out, and after a whole bunch of completing the square and simplifying, we get this equation, and we get this equation. So you can find the V1F by simply looking at the ratio of the masses times V1I, and the ratio of the masses times V1I for the V2F. Okay. There's special cases as well, which we'll do in class, and we'll talk about what those special cases look like. So, and actually, I should probably do this as a separate video lesson. So the key here is that these equations assumed that one of the objects was stationary. Okay. So how does this help us? Here's how it helps. Using the algebraic method, where one of the objects is stationary, you get these 2 equations. Okay. One of these objects has to be at rest. Now, in our question that we had, not both objects were not at rest. V1I was 2 meters per second, and V2I was 0.2 meters per second to the left, or negative 0.02 meters per second. So here's the question. Let's pretend that the second object was stationary. So we're going to change reference frame. Now, when we're changing the reference frame, what we're going to say is that V2I was 0. It's stationary. And if it's stationary, how fast does it look like, or if you are on that block and you think that you're stationary, how fast does it look like you're getting, or that other object is coming towards you? Well, the one object is moving towards you at 2, and you're moving towards it at 0.2, so it's going to look like 2.2 meters per second is the speed of that first block. And you would think that you're stationary. Forget relativity. We know it's 2.199999, but that's besides the point at this point. So here's the thing. When we did this, we added 0.2 to V1I. Okay? Clearly, because they were moving towards each other. So it appears that if you think that one object's stationary, it would just mean the other object is coming at you at 2.2 meters per second. So we added the 0.2. So now let's use the equation. Let's find out what V1F is. Well, V1F is M1, which was 3, minus M2, which was 1, over 3 plus 1, which is 4, times V1I, which is 2.2, and we get 2 over 4 times 2.2, which is 0.5 times 2.2, which is 1.1 meters per second. That's not our answer. That's not what we got. But now you have to remember, we added 0.2 to V1I in order because we changed the reference frame. So this is in the reference frame that the other object is stationary, but the other object is not stationary. So since we added there, we have to subtract the 0.2. And so V1F is 1.1 subtract 0.2, which is 0.9 meters per second in the normal frame of reference. And that is the answer. Let's try for V2. V2F equals, so twice the mass 1, which is 3, over the total, which is 4, times 2.2. So that's 6 divided by 4 times 2.2, which is 3.3. And then this is in the other frame, so we have to subtract 0.2, which is, so it's 3.3 less, because we added it over here, so we have to subtract it off here, is 3.1 in the frame that's watching this event happen. And it works. This is super fast and super easy. It's sometimes tricky to think about the change of reference frame, but it's really nice to do. So there you go. It's a long lesson, I'm sorry, but you have 3 methods for solving these complex problems. The algebraic method, write out the momentum equation, write out the kinetic energy equation, rearrange, substitute, use the quadratic formula, get the answer. You could start by writing the momentum, kinetic energy, use Wolfram Alpha. Find out where the intersection is, write the solution. Remember, you always get 2 solutions, the initial conditions and the final conditions. The third method is the change of reference method. And in the change of reference method, you are then going to look at the situation. You are going to either add or subtract the initial value and then do the opposite to get it back to the frame of reference. So if these were both moving in the same direction, you would subtract to get the relative motion. And then here you would add. Okay? Let's try all 3. So as I pointed out, for your lesson, you are going to do this. You're going to try questions 1, 2, and 3 using Wolfram Alpha. And then for one of the equations, or all of them if you have time, do the algebraic method for, let's say, question 3 and change a reference. Or do the change of reference for all of them and check them, do the Wolfram for all of them and do all the algebraic for all of them. But the key is make sure that you can do each of those 3 methods. Don't leave it. Make sure you can do it. Okay. Good luck with those problems.